Welcome to our lesson on representational independence. Today, we are going to explore one of the most powerful principles for building software that can evolve and change over time without breaking. By the end of this lesson, you'll understand why keeping implementation secrets is crucial for evolving software, how to apply representational independence to build change resistant modules, how to design opaque data types that hide their internal structure, and how to transform brittle, coupled code into robust, evolvable systems. Let me start with the fundamental insight that will change how you think about module design. Good modules don't just work, they hide how they work. Representational independence is the principle that clients must not depend on how a module represents its abstract state. When you achieve this, you can completely change internal implementation without breaking any code that uses your module. Let me illustrate this with a simple but powerful example. Imagine we have a counter interface with three operations: increment, decrement, and get value. Now, I can implement this counter in two completely different ways internally. The first implementation, simple counter, stores the counter as a single integer. When you call increment, it does counter plus plus. When you call decrement, it does counter minus minus. When you call get value, it returns that integer. The second implementation, audit counter, stores two separate numbers: the total number of increments and the total number of decrements. When you call increment, it increases the increment counter. When you call decrement, it increases the decrement counter. When you call get value, it returns increments minus the number of decrements. Now, here's the crucial insight. Clients cannot tell the difference between these two implementations. If you call increment three times and decrement once on either implementation, get value returns 2. The behavior is identical even though the internal storage is completely different. This is observational equivalence in action. Two representations are observationally equivalent if every public operation yields the same observable result on both. A client that cannot distinguish one representation from another is independent of the representation. This means that if I have two different ways of storing the same information internally and clients can't tell the difference through any operation they can perform, then I have achieved representational independence. Now, why is this audit counter approach realistic? This is actually how many real systems work. They keep separate counts of operations for audit trails. You want to know not just the final result, but how many times each operation was performed. Yet, from the client's perspective, it's still just a counter that counts up and down. Now, you might be wondering why this matters so much. Designing software that survives changing requirements hinges on one deceptively simple principle: keeping secrets. A secret of a module is anything that can change without affecting the behavior of any possible program that uses it. These secrets are your safety net. They let you replace a data structure with a better one, optimize an algorithm for performance, add caching or compression, or fix bugs in internal logic, all without triggering a cascade of edits across your entire code base. Think about this for a moment. How many times have you been afraid to refactor code because you knew it would break dozens of other parts of the system? Representational independence eliminates that fear.